Okay, everyone, sorry for the delay. So the last speaker this afternoon is Guillermo Henry from UBA and Instituto de Estudios Matemáticos Luis Santalo. He'll speak about the Yamabe equation under constraints. Guillermo.
Okay, thank you very much. I would like to thank the organizer for the invitation to speak in this session. Okay, Paolo and Jimmy already talked about this equation, but let me recall it. So in our setting will be a closed Riemannian manifold of dimension always 3. So in this setting, the Yamabe equation is this elliptic nonlinear PDE, where in the linear part is in the left-hand side is a conformal Laplacian, where here SG is a scalar curvature and HG is a dimensional constant. And in the right-hand side, the exponent is Pn, which is a critical symbolic exponent. We say that a solution that changes signs is going to be a nodal solution, and the zero set is going to be the nodal set, and we denote it by NU. So it will note that a positive solution of the Yamabe equation are related with constant scalar curvature metric in the conformal class. So for instance, if U is a solution, a positive solution of the Yamabe equation, then the conformal deformation of the metric G by the conformal factor U to the power of P minus 2 is going to be a metric of constant scalar curvature with the parameter C. So, however, nodal solution doesn't induce a Riemannian metric. They induce a singular metric, such that in the complement of the nodal set, there are constant scalar curvature metrics. So, in this talk, I would like to talk about some existence results about the solution of the Yamabe equation, but I am going to mainly focus on nodal solutions other than in positive solutions. Okay, we are going to use two approaches. The first one is given a compact subgroup of isometry, trying to find a solution that is invariant by the group. For instance, so for example, on the sphere is well known that positive solutions, all the positive solutions are radial, and also since the 70s, it's known that there is no sorry, but and it's well known from the 70s that there is no radial nodal solution of the sphere of the Yamabe equation. But in the 80s, Dean he found out this family of nodal solutions that are invariant by the product of orthonormal groups. And also they found a sequence, an infinite set of solutions that the energy tends to infinity. The other approach is given a suitable hypersurface or a foliation on the manifold, trying to find a solution that is constant along the hypersurface or along the lip of the foliation. But in particular, I want to discuss some results where this foliation is a foliation induced by an isoparametric function. And in order to produce nodal solutions, we're going to use the second Yamabe invariant, which is a conformal invariant, which is related or induced by the second eigenvalue of the conformal Laplacian. This second Yamabe invariant was introduced by Hammond and Umbar in 2006. Okay. The solutions of the Yamabe equation are critical point of the so-called Yamabe functional, which is this functional, which is easy to see that this is bounded from below. So we can make sense to define the infimum of the Yamabe functional over the Sobolev space. And actually, this infimum is a minimum, and it is attained by a positive smooth function. So, so this implies that at least we are going to have a positive solution of the Yamabe equation. This is the solution of the, actually, this is the solution of the celebrated Yamabe problem, that is due to Yamabe, Trudinger, Obam, and Shane. So, which is the relation of the Yamabe constant with the eigenvalue of the conformal Laplacian? So, the sign of the eigenvalue of the conformal Laplacian is an invariant of the conformal class. In particular, the sign of the first eigenvalue is equal to the sign of the Yamabe constant, and it determines the sign of the scalar curvature in the conformal class. I mean, for instance, if the Yamabe constant is positive, that is going to happen if and only if there exists a metric in the conformal class with positive scalar curvature. So, for instance, when the Yamabe constant is not negative, then the Yamabe constant is going to be the minimum of the first eigenvalue over the metric in the conformal class with volume 1. So the Yamabe constant is a kind of energy threshold for solutions of the Yamabe equation. All the solutions are going to be above the Yamabe constant. And also for another solution, we're going to have another threshold, which could be it might be a little bigger than this number, no? To the power 2 over n, the Yamabe equation. And this threshold is going to be the second Yamabe constant that I mentioned before. So let me define the second Yamabe constant. So it's going to be the infimum of the second eigenvalue of the conformal Laplacian over the matrix of volume 1. So when the Yamabe constant is non-negative, in that case, the second Yamabe constant is going to be bounded from below by this number, no? But what I said before, if U is a nodal solution of the Yamabe equation, then the Yamabe functional in U is going to be greater or equal than the second Yamabe constant. Okay, so in general, the second Yamabe constant is not attained by a Riemannian metric if the manifold is connected. But Am and Humbert, they prove that if this constant is attained, then it's going to, in some sense, that I'm going to say later, then there exists another solution, such that the Yamabe functional in U is going to be equal to this constant. So, and also they found some sufficient conditions for this whole, and they found that when the manifold is not locally conformally flat, if the Yamabe constant is zero, then the dimension has to be greater or equal than 9, or if the Yamabe constant is positive, no, then the dimension have to be at least 11. So in those cases, the second Yamabe constant is attaining, and we are going to have a nodal solution of low energy. Okay, so let me tell you briefly some other results that about nodal solutions that are obtaining with different approaches. For instance, this about of Del Pino et al., which are multi-peak nodal solutions that are they construct this solution using bubbles in Rn and in the sphere, of course, and or this about over Bertois bubbling up solutions, no, where here you is a positive solution and this is a bubble, but this is for the subcritical Yamaha equation, not the critical. This very nice result of Fernandez and Petean that is for the sphere, and given an isoparametric foliation of a degree different of 1 and any integer k, they found a solution, a nodal solution that such that the nodal set has exactly is exactly k leaves of the foliation, of the isoparametric foliation. Of course, there are a lot of results about nodal solutions. Here I put only some of them. Okay, so let me tell you a little bit about the Kibarian-Yamabe problem. So when you have a compact subgroup of the isometry group of the Riemannian manifold, then it consists finding Xi invariant solutions of the Yamabe equation, positive invariant solutions. Or what is equivalent is to find a constant scalar curvature in the Xi conformal class. The Xi conformal class are the conformal deformation of the metric Xi by functions that are invariant by the group Xi. Oh, okay, there are there are metric such that Xi belong to the isometry group. So in that setting, it makes sense to define this the so-called Xi the Kibarian-Yamabe constant, which is the infimum of the Xi of the Yamabe functional, restricted to the Xi invariant Sobolev space. So what is proof is if this constant is achieved, then we are going to have a positive Xi invariant solution. Okay. So let me let me define in order to state the word on site this. So if x is a point in the manifold, then we define omega x at the infimum of the integral such that the covariant derivative of the Weil tensor at that point is not 0. So for instance, when the manifold is locally conformally flat, then in that case omega is infinite in all the manifold. So, and if the manifold is not locally conformally flat, then there are going to be a point where the Weil tensor at this point is different of 0. So in omega x is going to be 0. So so this is showing result with Farid Madani. If you have a compact subgroup, no, the symmetry group, that the action is not transitive, and if you have and the conformal class and symmetric with non-negative scalar curvature, then if all the orbits are infinite, no, the cardinal of all the orbits are infinite, or you have a finite minimal orbit such that one of the point of the orbit or satisfy that omega x is less than a minus 2/6, then if the dimension, if the Yamabe constant is positive, and the dimension is at least 11, or if the MI constant is 0 and the dimension is greater than 9, then they are going to be a positive and a nodal G invariant solution. So this is a kind of secularization of the Humbert Hamann and Humbert result. So let me tell you briefly, roughly an idea of the proof. So so we defined that this the second equivariant Yamaha constant, which is going to be the infimum of the second eigenvalue of the conformal Laplacian restricted to the G invariant function. And we take the infimum over the metric in the G conformal class of volume 1. So it can be seen that if this if the second Yamaha constant, the second equivariant Yamaha constant is achieved by a generalized metric, that is a tensor, a symmetric tensor of this form, with U is a positive G invariant function that belongs to some LP. Then in that case, U have to be the absolute value of a nodal G invariant solution. So the point is look when this invariant is attained. So but to see this, the idea is to take a minimizing sequence of generalized metric and look where it converges to a minimizer, right? So, but so again, here the problem is it have some concentration phenomena, but under this the assumption of the theorem, we can see that we have this inequality that avoid the concentration phenomena, so we can extract, you know, a minimizer from a minimizing sequence. Also, under the same assumptions, what we have is that we can prove that the Hibby-Bougon inequality holds true. So, and this inequality, if this inequality holds, then the equivariant Yamaha constant is achieved. So that's what that is because we have, from this we have the positive G invariant solution. Also from this inequality, yeah, and studying the asymptotic behavior of the Yamaha of the first and the second equivariant Yamaha constant, we can prove that for products, for a Riemannian product of this type, where n is the dimension of the manifold n is at least 2, and the scalar equivalent of G of M is positive, then we are going to have again a nodal solution, a G invariant nodal solution. Okay. So let me say something about the isoparametric function. So for a Riemannian manifold, an isoparametric function is a function such that the square norm of the gradient and the Laplacian of f are constant along the level set of the function. So these two equations imply that the regular level set are parallel hypersurfaces of constant mean curvature. So it gives a nice foliation of the level set that the regular we call an isoparametric hypersurface to a regular set of an isoparametric function. So the level set of isoparametric function gives a nice foliation of the manifold. For instance, the isoparametric function, the classification of the isoparametric function in the Euclidean space we have three types: are hyperplanes, are spheres, or cylinders. So also in this, but for instance, the classification for the sphere is a little bit more involved, and they have a very long history, and it was recently achieved by Chi in 2019. So in that case, it's very much the family of isoparametric functions. Okay, so but when the manifold is closed, we have okay, they have this. We say that the isoparametric function induce a foliation where we have the angular level set that are the isoparametric hypersurfaces, and the singular set that it can be seen that that they are submanifolds. And actually, this submanifold, if the codimension of this if the codimension of the singular manifold is at least 2, then there are minimal manifolds. But also the isoparametric hypersurface or the isoparametric hypersurface are tubes over either of the focal submanifolds. Let f be an isoparametric function such that the scalar curvature is constant along the level set of the function. No, that we know with SF, and we are going to assume that all the level set, not only all the level set, have dimension at least 1. No? In that case, we can prove that there is a positive and another solution of the Gamma equation that is a constant along the level set of the function. So that the idea to prove this is by improving a little bit the Kondrakov theorem. So in the case where with the solid space HQ1 F, where this is a solid space of functions that are constant along the level set of F, then in that case, if this K is at least 1, then we can prove that the solid space is going to be compactly embedded if this one of these inequalities is fulfilled. That is, but this happen. This always happen for the critical exponent Pn and of Q1. So this is going to be compact. So in that case, we can obtain minimizer from minimizing sequence of both the first and the second Yamabe constant. So it's an immediate consequence of this is when you have an isoparametric hypersurface induced by the functions such that of course the focal submanifold that are the critical levels that have dimension, or the connected component have dimensions at least 1, then in that case they are going to exist a nodal solution such that the hypersurface is included in the nodal set of the solution. And if the function that induces the manifold is proper, that does mean that the focal subset has a codimension at least 2. Then in that case, they are exactly S is going to be exactly the nodal set. And also we have the existential solve for products. this kind, where f is going to be an isoparametric function of the first manifold, no? And that in that case, if fg belong to the is constant along the level set of f, and h is and s h, the scalar curvature of n is constant, then there are going to be a positive annual solution that is constant along the level set of the projection along the level set of f. Okay. Okay. Thank you very much for your attention.
Are there any questions?
Let me ask you a question, if I can. Are there any general situations where you can build these kind of things, the function, isoparametric, an isoparametric function in a Riemannian manifold, so that the scalar curvature is constant along the level sets?
Yeah, because I think that for that you can in this okay, you can start with a constant scalar in a constant scalar curvature manifold, but if the isoparametric function, then you can when you can start, then you can deform the metric, no, by a function, by a conformal function that is constant along the level set of the isoparametric, and then you are going to obtain a manifold that satisfies that, and it does, and also it doesn't have a constant scalar curvature. That.
Okay.
Guillermo, another short question. Could it be interesting to start, let's say, with the nodal solution which comes from an isoparametric equation, and then perturb the metric a little bit and look for nodal solutions nearby?
Yeah, of course, yes, that would be interesting, but yeah, I don't know anyone thought about that, but
no, but it's just sort of just an idle question. You kind of wiggle the metric a little bit, see what you can say, I guess. I mean, but maybe in some examples, what could say something.
Yeah, I'm not sure, but yes, sure, it's interesting, but I don't know.
Okay. Are there any other questions?
I have a question. When you mentioned that the Yamabe invariant was not achieved by a metric, but you could say that it was achieved by a generalized metric. What did you mean by generalized metric?
Yeah, it was actually that's when it's attained by a generalized metric. By a generalized metric, I mean this a metric of this kind. That a metric of it's a conformal deformation by
you can be.
But yeah, it could be zero. So it's not a Riemannian metric. Actually, if it is in a connected, of course, in a connected manifold, if it's attained, then it has to be by a generalized metric. But for instance, in the sphere, the second Yamabe constant is not attained at all, neither for a generalized metric.
Okay.
So you are not going to have solutions by the second Yamabe induced by the second Yamabe constant. So in some manifolds.
Okay, thank you.
Well, if there are no further questions, let's thank Guillermo again.
Okay.